So the subject of today's webinar is fibre in focus, protecting multi-storey car parks using fibre optic linear heat detection. In this webinar, we'll explore the challenges of managing fire safety risks in multi-storey parking garages and how linear heat detection can overcome these. If at any point you have any questions, you'll see at the bottom of your screen there's a Q&A button, so do feel free to click that and submit any questions you may have for our panel. And we should pick those up at the end of the presentation. So today I'm joined by a panel of experts. Firstly, I'd like to introduce Bandweaver's Managing Director, Richard Cluth.
Morning.
Business Development Manager, Marian Oosterhuizen.
Good morning.
And finally, we're pleased to be joined by one of our European partners, owner of SenseTech, Hans Bronkhorst.
Hello. Hans's
team have built SenseTech into one of the leading companies for car park fire detection systems in the Netherlands and other neighbouring European countries. So he brings plenty of experience to our panel. So on the agenda for today, firstly, we will look at the common challenges faced in multi-storey car parks when it comes to fire safety. Then we'll review the state of play in the UK along with a relevant case study. Then a little broader across Europe. Next, the panel will provide an overview of fibre optic technology. And finally, we'll take a look at a real-world practical installation of this technology in a car park environment. Now I'm going to hand over to Richard. Over to you.
Okay. Well, thank you. Let me just make sure I've got that. Okay. Good morning. Thank you very much for the introduction, Sarah, and good morning to everyone. Thank you very much for taking the time to come to our webinar. I hope you find it informative, and I look forward to a good Q&A session later. So I'm going to start by having a look at what's the overall situation in the UK and Europe with regards to fire safety in car parks, and we'll look at what are the overall risks, what are some of the common risks. We'll have a look at a detailed case study of a fire in the UK to go a bit into more of the details and show how that pans out and how in this case the detection, suppression, firefighting worked and what were the learnings from that. We'll then have a look at the legislation around the UK and Europe, how that's relevant within the car park space, and we'll take a deeper dive into the Netherlands to really get into the details and see how that plays out. And the reason for choosing the Netherlands is we have a lot of experience, and we have Hans from SenseTech on the panel as well, which is a great resource for us. Moving through that, I'll start with the fire risks. I'll move on to the case study in the UK, then talk about the legislation, and finally technology, where I will then hand over to Marinus, who will go into more detail on the fibre optic linear heat detection technology. So multi-storey car park fires, they have a number of risks, and these vary a lot depending on the type of car park, the region, etc. So we'll talk in the generalities and some of the risks that are common across that. So starting with vehicle fires, one of the key risks in car parks is the vehicle itself. It can start, fires can start from a number of reasons within the vehicles. That can be electrical faults, fuel leaks, or mechanical issues, all some of the main causes. And we'll see some of the details of that in the case studies. As we'll see, one of the themes we've seen across the board is that vehicles are increasing in size, and so that's increasing the chance of the fire risks. With regard to electrical systems within the buildings themselves, multi-storey car parks often have extensive electrical systems linked to lighting, security, etc. And malfunctions, short circuits, faulty wiring are all issues that have led to fires in buildings and multi-storey car parks. The materials, both the vehicles and the buildings have a lot of flammable materials. This can be fuels, plastic, polymers, and these have been increasing over the years, giving more fuel to the fire. Arson and vandalism. Unfortunately, these can be susceptible to both arson and vandalism. Inadequate ventilation, smoke management. So especially in closed car parks, these can lead to the accumulation of toxic gases, which poses additional risks both for people in the car park and the emergency responders. And emergency responders, limited access for them in some cases. They can have issues accessing the different levels, which can hinder the response time and allow the fire to escalate dangerously. Similarly, in some cases, there are limited detection and suppression, which also can allow the fire to spread further than otherwise would be. And finally, we'll talk a little bit about electrical vehicles. This is with the rise of electrical vehicles, installation of a battery charging station. This is going to introduce new fire risks, which need to be taken into account. We'll start with the study of a major fire incident in the UK, and I'm going to look at the Echo Arena car park in Liverpool. A few reasons for doing this. One is this is one of the largest fires in car parks in the UK, and as a result, there's a number of comprehensive studies and materials that we can draw on from this to understand better what the issues and how this can be addressed going forward. So the UK Echo Arena, this was a major fire event that happened on 31st of December, New Year's Eve in 2017. More than 1,000 cars was destroyed, so it's a very, very large fire. So large that the building had to be demolished. There was major structural damage. And in fact, the fire burnt so fiercely that experts said it had the same characteristics as a major petrochemical fire, which led to total damages of more than £20 million or 24 million euros. So one of the largest car park fires in UK history. So we'll go through the details of the car park. It's a 8-level, open-sided, multi-storey car park. Capacity 1,600 cars, 24,000 metre square of surface area. This was built in 2007, so would not quite be 20 years old now. And there we can see the floor plan of one of the levels. That's actually level 3 where the fire started. So it gives you an idea of the scale of the car park. And we'll have a look at the timeline now to give you an idea of how it played out when the fire was detected, when it was how did the fire services handle it, and how long did it burn for. So the emergency services were first contacted at 4:42 in the afternoon, 16:42. They were on scene with 8 minutes. At this point, the fire was already burning quite fiercely. It was on level 3. The accounts were that it was already leaping across empty bays, and an additional vehicle was becoming involved every 30 seconds. So the fire was already intense at this point, but was believed to have been on a single level. About an hour, just over an hour later, the realization that it had spread to another level. It was a level 4. At this point, all the firefighting was only on level 3. And at this point, this was the start of when the fire really started to get out of control. And within an hour, all firefighters had withdrawn from the building, and the firefighting efforts were focused from the outside at that point onwards. The fire continued to burn for more than 40 hours and officially was declared. The stop message was sent 7:34 in the morning on January the 2nd. So it was a long and fierce fire. If we look at where was it detected and how, that gives us an idea to what systems were there, and perhaps some of the shortcomings. So the first alarm was actuated at 4:43. This was a manual call point, so this was a minute after the fire brigade were called on level 3. And then at 4:49, the first sensor picked up the fire, which was a multi-sensor in the lift lobby. interestingly, this subsequent analysis showed that the incorrect location was put in the fire panel. It didn't matter in this specific case, but it goes to show some of the issues that even with it you can sometimes not get the right location. So very important issues. And then at this point, there are no other sensors detected at any other levels. So they fought on this level, and that was the way it was understood until 5:52, when the CCTV was confirmed there was a fire on level 4, but no other sensors. So I think it's now we've seen the issue of the scale of the fire. It's good to have a look at the legislation which determined for this building and others around the UK, what legislation is involved in determining what the designs of both the building and the fire detection systems. And in the UK, the most of the research actually goes back to a study in 1968 held by the Ministry of Technology and Fire Officers Committee that was done 56 years ago. So a lot of the regulations and design and the way this car park and others designed went back to that research. And at the time, some of the base assumptions they made in both the design and designing the car park and the detection and suppression is one, that fire would not spread from one vehicle to another, which is clearly not the case in this case. There was a lot of flashover from one vehicle to another, and also that fire brigades would arrive in 3 to 4 minutes to get the situation under control. I think with modern traffic, etc., that's not a realistic expectation. In this case, they were there 8 minutes on a New Year's Eve. I think most people say that's pretty respectable, but 3 to 4 seems overly optimistic for most cases. And all of the requirements based on that, there hasn't been any changes since 1968. So that we'll look at the conclusions of the report, but I think there was a lot of questions as to whether that should be updated. So if we look at some of the observations and recommendations from the various reports written on this fire, one key observation, as we said, is car sizes have increased significantly since 1968. And so there's a lot less space between the cars. And that's one of the key factors for the flashover. The other thing, as they're bigger, they also have a higher flammable contact, a higher fire load than 1968. So again, the fact they're closer together and they've got the higher fire load, this doubles up on the higher risk of flashover. Different materials in the car. One of the aspects that changed is that petrol tanks now made of plastic. In this case, if the fire temperature gets up high, these can melt and lead to running of fuel along the floor, which is what happened in this case, which was another cause for the spreading of fire. The original modelling done by BOA does not replicate what was seen in this scenario. And as well as the flammable materials in the car, there's much more flammable materials in the building. So everything led to a situation which led to this inferno, which probably wouldn't have been envisioned based on the material seen in 1968. So some of the conclusions could have been drawn from this is that a lot of people feel that the legislation does need updating to reflect the changes in vehicles, buildings that we've seen over the last few decades. Looking forward to electrical vehicles. So this is something for the future with the different fuel types, the charging stations. It changes the risk profile, and this is an example of something work our partners at SenseTech are starting to look at and integrate our technology into this. But something equally the legislation will be looking at. In the UK, had another fire at Luton Airport, October 2023, which again is increasing the pressure. There's been some initial discussions around this, but in due course, the reports will certainly come out that will, obviously have more recommendations. So I think we are in a climate that is likely to see that. So if we move on to Europe, look at the regulations there. Europe's combination of different countries, obviously. So each one will have its own arrangements. So we'll sort of start off by looking broadly what are the similarities in Europe, some of the frameworks, and then we'll do the deeper dive into the Netherlands, look at the regulations there, and really show, you know, how does that result in the specific detection technologies being chosen. So the regulations for multi-storey car parks, you know, as you imagine, it's very complex, very you know, number of different factors considered. We can see some of them here on the screen. I'm not going to go into the specific details, but as you can see, many considerations varying from the structure of the building itself through to, you know, suppression lighting systems and what firefighting equipment goes into the buildings. So a lot of different legislations, and you know, for this we need a lot of different bodies to manage this, and this can vary from national, pan-European. This can be sort of local government bodies through to international insurance companies, and all of these will have different recommendations and consultations on how the legislation is implemented in all the different areas. So it is a complex landscape, and so if we look at some of the commonalities between, you know, one of these are is the European standards. What is consistent across Europe are the EM54 certifications, and I'm going to introduce the relevant EM54 certifications that are appropriate to linear heat detectors and our fiber optic technology. So EM54 Part 22 is what is applicable to line type detectors. This covers copper-based systems, multi-point and fiber optic that Marinus will talk about later. What we do see is that, you know, these are consistent across Europe. They're valid, also highly respected around the world. We see Middle East, Asia, South America. They also take reference from the EM54 and often specified there. They're accredited by international agencies with high credibility. VDS and UL both accredit the EM54 22, and so it's widely adopted. So it does give some commonality, but it's not a harmonized standard EM54 22. So often additional regulations are required in specific countries. These are often based on EM54, but will have differences on that. So to give an example of that, we will look at the example of the Netherlands. So in the Netherlands, we have as we said, the building regulations. I'm not going to attempt to pronounce that. I'll let Marinus and Hans in the Q&A, if anyone wants to know how that's pronounced, take care of the building side and issuing the fire certificates. On the with regards to the different standards, the Netherlands Institute for Standardization, the NEN, develops the standards related to fire safety, including car parks, and these provide guidance on design and safety requirements across a wide array of areas. You can see here the fire resistant materials, ventilation, lighting, structural design, through to energy efficiency. The particular standard that is relevant to the ours is the EN 5525-35. This was put together in 2017. This references the EN standards, but it does have very specific features that are modified for the Dutch market. The linear heat detection technology is not specifically designed in that, and so the way they manage this is they use a fire pan test that has to be carried out in each installation at the commissioning stage. And the Marinus will go into some of the details of the fire pans and how that's done, so I won't go into the details there. There are some other general guidelines around ceiling height. You should go above 7.5. The sensing points are generally 7 meters apart on a flat ceiling, and it doesn't specifically reference the response times, but the system does have to respond while the fire is still burning, and it's a small it's a small fire, so it's actually quite challenging. So this does have a big impact on how the technologies, which technologies can manage this. And so if we look at the technologies used in car parks, smoke detectors are not effective. Vehicle or exhaust emissions and dust can either cause these to block or to false alarm. Also, moisture and humidity in open garages means that this is not widely adopted. In the case of linear heat detectors, the digital analog copper-based cables generally can't pass these fire pan tests. They're not sensitive enough. We'll see an example of tests and what sort of temperatures they get up to, how early they trigger, but it generally means these aren't applicable in this market space because of the legislation. Air brace pressure sensors, in theory, probably can detect in this environment, but they're very short range, and you'd need too many controllers, so they're not practically usable in this scenario. So the two main technologies that are used are the multi-point line type detectors, and these tend to be used in the smaller car parks, less than 7,000 meters squares, where you can have the spacing closer together. And in the larger car parks, where over 7,000 square meters, it tends to be the fiber optic, which has continuous monitoring, as we'll see, and the economics become very favorable at the larger case. So there's my sort of brief introduction as to some of the issues in Europe and UK, and I will now pass back to Sarah to continue.
Thank you very much, Richard. I'm now going to hand over to Marinus, who will cover the introduction to fibre optic linear heat detection technology. Just a reminder before I do, if at any point you have a question, just hit that Q&A button on your screen and you can answer any questions that will be covered by our panel at the end. Over to you, Marinus.
Good morning, everybody. Thank you for the introduction, Sarah, and thank you, Richard, for having the slide so far. Just a brief introduction to fiber optic linear heat detection technology from me, with a little case study in the Netherlands at the end. So fiber optic linear heat detection systems use DTS technology. There's quite a lot of abbreviations here that I always struggle to pronounce properly, but DTS stands for distributed temperature sensing. And then the system uses telecoms grade optical fiber, which is the same telecoms cable we use in daily life when we use broadband. The technology is based on OTDR, which again stands for optical time domain reflectometry. The key point to take away from this is that the fiber is the sensor. No point of specific fiber sensors required, and that is really the most important thing to take away from this. So how does it work? The control unit will send a laser pulse down the cable. This cable will interact, or this laser will interact with the cable and will send back a signal, backscattered light. And the time it takes to send it back will give us an accurate reading. So typically it's between 0.5 meter and 2 meters. For fire detection, we typically use 1 meter. And this system works on a time of flight principle, which is similar to radar. The fiber is the sensor, so no dedicated sensors required, and it gives complete coverage along the entire cable length. As it is a single cable, it also gives you simple installation and planning. So here you can see the cable overhead in a parking garage. So the key component is the cable. No maintenance required. It's totally a passive sensor. There's no moving parts. It's not susceptible to corrosion, and it's got a design lifetime of more than 30 years. And in some cases, these cables exist for over 50 years. It's also immune to electromagnetic interference. No infield power or comms required. So it is just the cable that is needed. It's very lightweight and flexible, as we will see later. And the cable thickness is 3 to 5 millimeters, which makes it very easy to install. So there's now a short video, and I hope this works correctly, with an introduction to the fire laser unit. So I hope everybody was able to see that video clearly, as it gave a good example in a test environment of the control unit and the cable. This is an example of a fiber optic linear heat detection system architecture. It shows you the parking garage, the cable going back to the control unit, and from the control unit via relays, in this case, to a fire control panel. So here we got two examples, one of linear heat detection and one of a multi-point line type system. In the case of the linear heat detection, it will show you an example that it continuously detects everywhere. So I'm not sure why this is not working correctly at the moment, but it should show you that a fire is wherever the fire is located, it will detect. So the cable is the sensor, and it doesn't really matter where the fire is. And in the case of the multi-point system, is the fire is in between the sensors, it will take longer to detect and delay a response. So you can see here, yes. So we also have three types of different alarms. We have a deviation alarm, which deviates from an average temperature. Then we have a rate of rise alarms that will detect a change in the temperature in degrees per minute. And we have a maximum temperature set, the temperature which point the alarm triggers. And we also have something called smart zone. Software is completely configurable up to 1,000 zones with complete flexibility. So you can put a stop and starting point in. You can put different alarms in the different zones, and it is completely flexible. A little bit about maintenance and reliability. The cable, as we already said, is completely passive. There are no moving parts, no apertures, and it's got a design life of more than 30 years without a maintenance schedule. It's a single cable installation. There's no power required, no comms network, and it's not affected by the environment. So dust or particles don't affect it. In case of car parks, there's exhaust fumes, no electromagnetic interference, and humidity is also another point. So an MTBF or mean time between failures of 29 years, which is Telcordia standard, which is a telecoms standard. So it's a fully approved system, which EN54 Part 22 is the main one, but there is many other international standards that we comply to. So next we move to the Netherlands with a car park case study. And first of all, we're going to watch a short video that Hans, the owner of Senstek, has done for us. And you see a practical installation in this case.
Hi, we're here in the parking garage, one of the many in the Netherlands that we have done so far. What we normally see in the parking garage is that you have the parking lanes that are about 5 meters deep, driving way about 6 meters wide, then you've got another parking spot. And normally we place the cable around about a meter in the parking spot. Here you see the cable, it's now T-clips in this case, but it's only it's done with steel cable. Here you see the cable, and when we go to the other side, this cable is located here. It makes it spacing of about 7 to 8 meters. When we want to make an alarm or want to make sounds, it's off air down the cable. Hi, this is the location from the controller. We normally place it in a cabinet like this, where we can open the deck as well. So here you can see the connections that we have made in the cabinet, and cables are located here.
Thank you, Hans, for that example, of which he has done many in the Netherlands. And the following is a short example of a particular parking garage called P10 in Amsterdam. It's an indoor car park, and of course, car parks are very dusty environments with exhaust fumes, so smoke detection is not really an option. In this case, it was a redundant loop they did, as you can see on the drawing, with a total length of nearly 7 kilometers. And the spacing between, as you already indicated, is about 8 meters between the cables. So here you can see some examples of the cable installation with the varying heights. It is quite challenging, but because the cable is very flexible, it is not a problem at all. As Richard already mentioned, in the Netherlands they do a firepan test, where they also measure the wind speed. All systems must pass this small firepan commissioning test. It's a 50 by 50 centimeter pan with ethyl alcohol. And the ceiling heights vary from 2.5 to 3.5, and sometimes even up to 5 meters when they're in particular environments. So they will set the fire pen test at certain parameters, an absolute temperature of 50 degrees, from 10 to 13 degrees, the rate of rise, and a deviation at 20 degrees. This is an example of a system commissioning test. I will run that in the background so you can see how it runs. In this example alarm, it sounded within 25 seconds on the rate of rise alarm. You can see on the picture on the left bottom, the fire pan is situated in the worst possible scenario, so 4 meters away from the cable. And in the graph, you can see there's a detection at a 10-degree rise after 25 seconds. So a little bit about bandweaver now, some key details. Year of foundation is just over 20 years ago. So in 2022, we were exactly 20 years in business. We've installed since then more than 8,000 systems and a total length of over 60,000 kilometers of fiber optic cable, which is an awful lot. Number of people is just over 300, which are located all over the globe. And the key technology is distributed fiber optic sensing. DTS is the distributed temperature sensing. We also do something called DAS, which is distributed acoustic sensing, but it's a completely different technology. So as you can see, we've got locations all over the globe, whereas I'm based from Guildford, our UK office. We've got an established international customer base, from Honeywell to Turkish Airlines, Schneider Electric, and many of them are repeating customers. Conclusion so far: car park and fire regulations are changing as vehicles also change, as Richard showed clearly. The technology is robust and reliable with a very low cost of ownership. If you bear in mind the cable lasts for 29 years plus. Fiber optic linear heat detection becoming more and more prevalent in car parking garages, and fiber optic LHD provides the most comprehensive coverage. And then last of all, Bandweaver and Senstek have extensive experience in fiber optic car park LHD applications. So with this, I hand you back to Sarah for the questions. Thank you.
Thank you very much to both of you for the presentation there. We've had a few questions about will the presentation be available? Yes, the webinar is being recorded and it will all be distributed post-webinar, so don't worry too much about what you may have missed. And I gather those videos might have been a little slow when sharing, so you will have a chance to review those again. So we have our panelists back, and we've also been joined now by Hans. Welcome. So I'm going to run through the questions that we've received through the course of the last 45 minutes or so. I'm going to direct them all at Richard, although should he wish to delegate to the rest of the panel, he will do so. So let's start with, what is the recommended cable spacing in car parks?
So yeah, very good one. Well, thank you, Sarah. Yes, no, it's a good one. So as you know, we're located in the UK, as Marinus mentioned. So the spacing we use based on BS 5389, which is a UK standard, which talks about conventional point heat detectors, which should be 5 meters with 3 meters apart. But because we have continuous coverage the whole long way of the cable, if you do the maths, this means we can move to 5 meters between sensing points, which actually means the cables are 10 meters apart. So that's what we recommend from a UK. I mean, we have, we see our partners all around the world. They use local regulations. I think Hans talked in his video there about being 7 to 8 meters. Is that typically what you do, Hans? You alluded to it was related to the usually being a meter inside the spaces. What do you normally see in terms of spacing in the Netherlands?
Yeah, this 8 meter is quite standard, and that has to do with the structural sizes that you have in a parking garage. If you place it like the way I was mentioning in the video, then you have every cable is actually above a parked vehicle, and you see a repetitive distance of 16 meters, which is 2 parking bays of 5 meters each, and a driving way of 6 meters. So that makes it 16 meters. So then you have a repetitive distance of 8 meters or 16 meters. And that is where it's coming from.
Okay. No, that's interesting. If I would say, and if I look across this installation, other installations, what we tend to see as well is it depends on familiarity within the specific country or sector. So some countries where we've seen the technology be widely deployed, the consultants will often be more comfortable with stretching past some of what the official recommendations are. So, for example, another ceiling height is something that's discussed, and according to the regulations, we can go up to 10.5 meters in some cases, but we have seen dispensation in certain ones where multi-levels, and they've seen multiple extras, people will go above that. So it does vary, but hopefully that gives a feeling for what it can be.
Lovely, thank you both. A few people have asked similar questions, so I'm going to consolidate this one. What happens if the cable gets damaged?
So that's a very good point. We didn't address it in this specific presentation. We had a lot to cover, so we didn't go into all the technical details. But you can configure the system in what we call a loop configuration, which means you've got access to both ends. So in the event that the cable is damaged, the system still can continue to operate up to the point of damage. It lets you know that you've got a damage, and you can go and repair that. But in the meantime, the system continues to operate without any issues. But you've got damage. I mean, Hans, do you want to talk about examples? I think in the past you have had something with high trucks catching cables before, and the practicalities in the field. Have you seen many examples of where there has been cable issues?
We have seen some damages, and not only with this cable type, but with other cable types as well. And that mainly has to do with too high vehicles entering garages. Normally you have a protection that hangs over the entrance on a certain height, and when that is not correctly mounted, then it can happen that a vehicle that is too high can enter a garage. And yeah, of course, when it can hit the ceiling, it will hit everything on the ceiling, including the cable, but lighting and everything as well. And we have seen that a few times, but it is normally it can be avoided by placing the protection in a good way.
Lovely. Can a system detect multiple fires simultaneously?
Yes, absolutely. I think it's measuring that, as Marinus showed in his excellent sort of introduction there. It makes the cable sensitive along its whole length. So you're dividing it into sections of 1 meter. So you could have an event every 1 meter if you wanted it. It can detect them all independently. So yes, it has the capability to measure all independently. And then so you got that, but then you've got the other factor is how do you interface with the fire control panel? So you set up zones. If your main interface is the fire control panel, you would just see the information from that. But yeah, you could still detect multiple fires. And so, we would hope, if we go back to the Echo Arena car park, where there was no detection on the level 4 other than CCTV, which can be a fire detection system. I'm not sure if it was in that case. We would have hoped that we would have seen that much earlier on, and a lot more information as to where the fire is spreading, which often people use, not so much in car parks, but in larger tunnels. They will take all of this information and input it into the building management system and use it to work with the ventilation systems, because they know exactly where the fire is spreading, etc.
Thank you, Richard. You mentioned there about integration to the fire panel. How is the controller integrated?
I'll pass that to Hans. Do you want to say how it's typically done in the car parks in your scenario?
Yeah, well, when you look at EN54, you're obliged to use relays. So we have a total of 50 relays on the fire laser controller, of which the first 6 are fault relays and the other 44 are free to use as fire relays. So each zone is being given a fire relay number, and that relay is connected to the fire panel via an input module.
Yeah, and I think that's what we haven't covered it in this presentation. This is focused on car parks, but we do cover a lot of other sort of fire detection applications. And what we see is we tend to see, I guess, what you would classify as the smaller sort of single or 2 unit type installations, car parks, warehouses, factories, etc., where it tends to be just integrated with the fire control panel. But where we see larger installations, either very big petrochemical warehouses, tunnels, etc., often they want the extra information, and so we use the Modbus output, which goes into a SCADA software or building management, and then they get extra functionality and visualization. But as Hans said, the EM54 does dictate that if that it has to be output by relays, but as well you can do Modbus if you want that additional information.
Great, thank you. Is it possible to have more than 4 channels per controller?
Very, very good question. In the technology, so I'll answer first from the technology's point of view, and then kind of caveat that with how that fits into the approval. So the technology can do more than four controllers. We can do up to 16 channels on this one, but it's only looking at one channel at a time. It sort of switches between them, so the others are not detecting during that period. So when we did the approvals, we took the decision to do 4 channels as a maximum, so that you're rotating through them quickly. We do quick measurement times, less than 5 seconds per channel, so you're cycling through very, very fast. So as a fire detection system, certainly an approved one, 4 would be the maximum number of channels. But in terms of I guess we haven't discussed range of the systems. I'm not sure if this is an upcoming question, but one of the variable factors is, the systems have different ranges. They start at 2 kilometers and go up to 10 kilometers per channel. So, for example, for a 10-kilometer 4-channel system, that's 40,000 measurement points, 40 kilometers of coverage you can have. Whereas for a 2 kilometer, that's 2 kilometers for 8,000. So there's still a lot of variability. And if it doesn't, if you're thinking, well, maybe this doesn't cover my installation, there are views to getting longer range systems as well.
We have another question here. You mentioned that the system can measure down to 0.5 meter, but you also mentioned that the standard measurements are 1 meter. Could you just clarify that?
Yes. Marinas, do you want to take that? I know you covered that in yours, or do you want me to?
I would prefer it if you did this one, Richard, because
Okay.
the spatial resolution, I'm still mystified sometimes.
Okay, yeah, and that's good. Well, that's good. Good news. Yeah, and it is something that for people seeing for the first time, it can be. It's a new concept, and getting data point every half meter along the cable. It's a lot of information, a lot to process. So generally we don't use that for fire detection, because it doubles the amount of data management you use. If you're trying to access and manage and store the data, it doesn't really bring any additional benefit in terms of how quickly you detect the fire. Typically, we do 1 meter is that, so we have it every 1 meter, and we found that's the sweet spot. But as Marina said, it can be quite a confusing sort of landscape. So for example, we found some companies, for example in Switzerland, they've defined it as they want to have 3 meters as the standard, and we're not really sure why they've chosen to broaden that to 3 meters. I think some systems maybe need that to have the sort of stability. We don't. We would say that decreases the sensitivity of the system with no additional benefit. So we found that the sweet spot across all of the systems is for a 1 meter, having the measurements every 1 meter.
Lovely, thank you. I have a question here. It was mentioned that there is no maintenance, but what are the testing requirements for the system?
So in a practice, Tams, what's the sort of I guess both the initial ongoing testing and ongoing? What do you typically have to do in an installation?
Well, in the Dutch market, you must perform a functional test on every zone that you've programmed. So if you have a redundant loop going through 10 zones, you have to make an alarm in every zone on an annual basis. And you have to inspect whether the cable is still mounted correctly.
Okay.
And the fire test that we do, of course, you can do a fire pan test, but as I showed in the footage, we normally use a hot air gun to just heat up 20 to 30 centimeters of cable, and then we see an alarm rising. So it's very quickly to be done.
Okay, and you do that on an annual basis with the hot air gun in the car park, doing each zone on a
Correct.
Yeah.
Yeah.
It's interesting because across different industries we see different requirements because the alarms are done in the software. It's not a hardware thing. In some cases, people will accept a test being done outside the zone to show the functionality because it is all software based. So we do see that in particularly false ceilings or something where it's hard to get in there and do the testing. That's one of the advantages in that. In some scenarios they do allow the testing to be done outside of the zone, but Hans is saying there in that case they want a physical measurement in each zone. So it's interesting that it does vary from region to region. But yeah, I mean, just going back to the cable, I think it's Marina's made the point very well there. But it's a passive sensor, so short of getting hit by a car that's come is too high and there's really nothing much you can do about that. As Hans said, other cables get just without that. These cables, as we said, can last for more than 30 years and often have been. If you look at the early telecoms cables that were put in more than 50 years ago, they're still going because there's no moving parts, no corrosion, really nothing to erode the cable. So it is if you get it right with the installation, it is maintenance free from the cable point of view, and the unit as well has no moving parts, no fans or anything. So typically running full blast, those are also last well in excess of 10 years, with the MTBF according to Cordia standard being 29 years. So these can last for a long time.
I think I'll ask this one next because it's sort of relevant to what you've just said. Have you considered different types of fiber cables for this, and what's the most important thing to consider when choosing a cable?
Yeah, so there's two key factors on this, or three, I guess. One is the strength of the cable. You need to have it, strong so it can be rust. Two, flexibility, lightweight, easy to install. But then the third factor is, it has to be responsive. So you need something relatively lightweight so that the heat conducts very quickly to where the fiber core is. So we've we've worked that, we developed the fiber 580 over a number of years, and that's really the sweet spot of all of those. So that is the cable we use in 99% of our installations. If the approvals are required, the approvals are the cable and the unit together. So there's not really any choice in that thing. If we do installations outside of the where it's EM54, whether it's a non-fire detection or some applications just don't have those stipulations. Other cables are used in some cases, but it's pretty unusual, and it tends to be very specific requests, like it might be something with a specific corrosion resistant to a certain fluid, or in some cases operating in very high temperatures. So our cable as standard is rated to 85 degrees C, so it operates fine in conditions up to that, which covers all normal sort of environmental conditions. But some people in a furnace, for example, might have standard operating conditions of over 150 degrees, 200 degrees C. So they want a cable that's rated to 300 degrees C. So we may consider in that cases. But the short answer is for fire detection, we use the Fire 580, and it's proven to be an excellent cable for that.
Excellent, thank you, Richard. I think we may only have time for one more, but I think it's potentially the most important question. How do these solutions address the need for a swift response and intervention in the event of a fire emergency, and what measures are in place to ensure timely activation of suppression systems? So essentially, what difference would it have made in that Liverpool fire?
Yes, and that's I think the big key question is how early would it have detected, and what action could have taken there. So I believe from there they didn't have a sprinkler suppression system, so I'm not sure that there was a suppression system that would have acted earlier. If there was one, then surely that would have been activated earlier. And what we see in certain larger installations is because we have that detail where we can get down to the nearest 1 meter. Often the suppression system will be linked only to our technology, even though the installation may use multiple technologies, because we can really get down to that level. We say, right, turn on this sprinkler first, and then activate it. So you minimize water damage as well as getting in there earlier. So I think we would have, in the case of the Echo Arena, I think we would have detected it potentially earlier, because you could see when they came that the fire was already very fierce at that point. So I think we could detect it. So I think we would have got earlier detection. We certainly would have detected level 4 being much earlier than it would have. So the firefighting strategy may have been able to get up to the level above and get in there. So by the time they left, it was already multi-level, so they probably could have kept it to within a level, got there earlier. But if you're implementing, and often in different installations we see it integrated with more advanced suppression systems, where it is putting it out very earlier, and the fire services are not needing to be called. It puts it out much earlier, and also limits the water damage, that you can focus the suppression system to where the fire is at a small stage. So you're not turning on the whole floor. You can say, right, let's turn on this 10 meters. If you're starting to see it spread, well, when you say the system, then it automatically comes on at the other levels as well. So we see, where people are planning that now and putting advanced suppression systems, we're really seeing a different level of how they can fight the fires and catch it and suppress it much earlier.
Lovely. Thank you very much, Richard. Thank you to all of our panelists. That is all we have time for, unfortunately. You'll see our contact details up on the screen there, and we will be circulating the video and the whole webinar over the next few days. Apologies, we have no time to answer all the questions, but we have collected them, and we will be coming back to individuals should we be able to answer those after the call as well. So that just leaves me to thank Hans, Richard and Marinus for joining us today. And thank you all for joining us, and we hope to see you on our next webinar. Thank you very much.
Yeah, thank you very much, everyone. Thanks all for taking part, and thank you everyone for dialing in.
Thank you.